just take some nice points that you can easily tell on your graph and shift those down. What's B going to do? Right 2. So you take these points and shift each of those right 2. What happens on C? Left 1 up 2. And D. The negative reflects it over the x, so this point's on the x, it wouldn't move. Then we go right 2, up 3. If I take this one, flip it over the x, it goes down here, right 2, up 3. This one, if you flip, doesn't go anywhere, right 2, up 3. This one, if you flip, it goes up to 2.5. Right 2, up 3. So we don't have to have an equation for the original. We either need the equation or we need a graph. And then we can do our transformations. Okay, any questions about that? So the last piece we have to talk about is symmetry. And there are different types of symmetry. The first one, symmetry to the y-axis. So first, let me just think about a picture. Something that would be symmetric to the y-axis, think about like this graph. If I was a good artist, if I fold this piece of paper on the y-axis, would those two pieces overlap themselves? Yes, that's symmetric to the y-axis. What that means is both a positive and a negative x, so whether I'm at positive 2 or negative 2, we get the same answer. So think about like 2 squared is 4 and negative 2 squared is 4. Both the positive and the negative x giving the same y value. So it's symmetric over the y-axis. Symmetric over the x-axis means both a positive and negative y give the same x. So something like this. If I fold that graph on the x-axis, it overlaps itself. Positive y and negative y correspond to the same x value. Is that a function, by the way? No. So when we're looking at functions, we won't have to worry about symmetry to the x-axis. But if I just give you an equation, we'll check it. I think I'm going to do things that just a touch out of order from what's on your sheet. I'm going to go ahead and jump down to the last type of symmetry, and then we'll just come back and do these examples and check for all of them. Symmetry to the origin means if you replace the positive x with the negative x and the positive y with the negative y, you get the same thing. Okay, that sounds really confusing. You think about the graph. It's like saying if you have the point 1, 2 on your graph, you also have the point negative 1, negative 2. So you could change the sign on both the x and the y. If I think about what this graph might look like, this would be an example. In order for it to overlap itself, you have to fold it twice, over the y and the x-axis. So I'd have to fold it over and down before it would overlap itself. Does that make sense to everybody? In terms of how to decide if these things, if a function or an equation has symmetry, we have different options. If it's something we can graph, then we can look at that graph and tell. Sometimes it may not be easy to graph it, so we might need to use the equations. So what that means, if I want to check symmetry to the x-axis, okay, so if you look back at your definition, if it's symmetric to the x, positive y and negative y give you the same thing. So essentially what we're going to do is make the opposite variable negative. So I'm going to make my y negative. If this turns back into the original equation, then it's symmetric. If it doesn't, it's not symmetric. What happens if you do the absolute value of a negative? So this turns back into the original, so it is symmetric to the x-axis. If I want to check symmetry to the y-axis, what do you think we need to do? You make the opposite variable negative, so I make my x negative. Okay, is there anything I can do to that to make it turn back into my original equation? We can divide by -1, that just moves the negative over in front of the absolute value. So it changes it, but does it make it match? No, so this one is not symmetric to the y. I can't just make that negative disappear. I can move it around, but it won't go away, so it's not. Origin, you do both. You make the x negative and the y negative. Okay, I can't get rid of the negative on the x. The absolute value of negative y is the same as the absolute value of positive y. Is that the same as my original? Nope, so it is not symmetric to the origin either. Alright, let's try some more. Let's do B. So how do I check the x-axis? Opposite variable, so y negative. Is there anything you can do to make that turn back into the original? Nope, so this one's not symmetric to the x. How do we check the y? Make x negative. So the absolute value of a negative is positive. Oops. We said to only make our x negative. So does that turn back into the original? Yes. So that one is symmetric to the y. How do we check origin? Both negative. The y and the x. So is that one a yes or a no? Okay, let's do, let's go ahead and we'll do 2 more. And if we need more beyond that, I've got them on here. If we don't, we'll stop and move on. So C, to check the x-axis, what do you do? So that gives you 2x minus negative, so plus y equals 6. Does that match my original? No. To check the y-axis, so if I make my x negative, I get negative 2x minus y equals 6. Doesn't match, so it's a no. To check my origin, we do both. I could multiply by a -1 here. That would give me a positive 2x and a negative y, but it turns it into a -6. So does that match? No. So it doesn't have to have symmetry. All of them may turn out to be no here. It's not like a guarantee one of them has to be a yes. All right, last one. So to check my x, if I make my y negative, what happens if you square a negative? turns positive. So does that match my original? Yeah. To check your y, you make the x negative. If you square a negative, it becomes positive. So that one also matches my original. Origin, if I make my x negative and my y negative, you're squaring, so both those become positive and it matches. So that one is also a yes. So what we've seen is we can have all no's, we can have all yeses, or we might just have one yes that pops up. It's true that if both the x and the y are yes, the origin will automatically be a yes. It is possible to be symmetric to the origin and have both of the others no, but it's guaranteed you'll never just have two yeses. If you've checked two of them and it's a yes, the third will also be a yes. So you don't necessarily have to memorize the slide, just know how to check for symmetry, but you'll never work it and get two yeses and one no. If you've done that, you've got a mistake. All right, let's check from a graph, make sure we know how to look at a graph and check symmetry. And also, some terms that we might use instead. We talked about in terms of functions, even and odd. Even is the same thing as symmetric to the y-axis. So basically, whether your x is positive or negative, you get the same thing. Odd is symmetric to the origin. That means your x can be negative, and that puts a negative out in front of the y. You can't be symmetric to the x-axis if you're a function. Like we already said, that fails the vertical line test. So I want to know if these are even, odd, or neither. So even just means symmetric to the y-axis. Odd means symmetric to the origin, the O's go together. Or neither. So what would this one be? If I fold this on the y-axis, it overlaps itself, so it's even. What about this one? Odd. If you flipped it over the y, it would look like that. And then if I flip that over the x, it overlaps what we started with. If you flip it over the y, that piece goes there, this would go over here, this would go over here, and then if you fold that over the x, that overlaps this and this. So that one is odd. About this one? It is also odd. If you flip it over the y, it looks like that. Then if you flip it over the x, it overlaps that original. Okay. Just a couple more. Talking about how to check symmetry if it's written in function notation. What you can do is find f of negative x. So you're, instead of plugging in the negative for the x and the negative for the y and then doing the negative for both, we put a negative in for just the x. If it turns out to be the original function, that means both a positive x and a negative x give the same thing. So that means it is even, or symmetric to the y-axis. So if you plug in negative and you get the original, it's even. If you plug in a negative and you get the exact opposite, that's odd. And if you plug in negative and you don't get what you started with or the complete opposite, it's neither. So on this one, if I put in a negative x, if you take a negative cubed, is it positive or negative?
Negative.
Is that what I started with? No, because on the x cubed. Is it the same as multiplying the first one times -1? No. So this one's neither. C, if you put in a negative cubed would be negative, so we have a negative 5x cubed, minus negative, so plus x. Is that what we started with? No. It is the exact opposite, so that means it is odd. You are also welcome to graph these and look at your graphing calculator like we looked at these graphs and decide even or odd from there. So there's an algebraic way of doing it, and then there's a graphing way of doing it. I have more examples on here. Do we need them? We're good? Okay. So, a couple things. You have that assignment. You have the rest of class to work on that. Tomorrow, I want to do a quiz. I'm going to tell you exactly what's on it, though. It's going to cover what we've done this week. So this week only. So, remember we started with section 2.6. So part of the quiz is going to look like that homework on page 255 where you had those graphs and you had to answer all the questions about them. The first part of the quiz, I just took those graphs and I'll ask you, which one's the graph of the absolute value? Where is it increasing? Or what's its domain? Or those kinds of things like we had on that assignment. There'll be a couple of transformation questions and there'll be a graphing piecewise example. We'll probably do a graphing piecewise function example at the start of class tomorrow, just as a refresher before we take the quiz. So, and you've got time to work.